Okay. Good evening, everyone. I am Siddhartha Pramanik, a research scholar from Department of Mathematics, IIT Kharagpur. I am a TA for this course, Introduction to Abstract Group Theory. So, in this live interaction season, I will start solving some problems, and this is for your doubt solving season also. So, let me write down the problems first, then I will solve them. Okay, so the first problem is let G be a group and take two elements, say G and H from G. Okay, then we have the following results. First one is if you take G inverse, then this is an element of G. Then again, if you take inverse of this, then this is nothing but G. And second one is if you take the element GH and take inverse of this, then this is same as H inverse G inverse. So in this case the order is changing. Okay, and the third one is if you take the element GH G inverse and take its nth power, right, then it is same as G H power n G inverse, and this is true for all integers n greater equals to 1. Okay, so I hope you have understood the problem correctly. Okay, let me start by solving the first one. So in first one, we need to prove inverse of G inverse is same as G, right? So we need to prove inverse of G inverse. This is same as G. Now, what is the meaning of that? So that means if we take G inverse and multiply with it inverse, which is G, and in the that should be same as the identity element of the group, right? And on the other hand, G times G inverse, this also has to be the identity element of the group G. But this is already true, right? But this already holds. Why? The reason is inverse of G is G inverse, because inverse of G is G inverse. So we are done. Okay, I hope this is fine. So let's move on to the second problem. So in second problem, we need to prove the inverse of the element GH is nothing but H inverse G inverse. Okay. So we need to prove inverse of GH is same as H inverse G inverse, right? So what does that mean? So it means if we multiply GH by this element from both sides, we should get the identity element of G. Okay, so let's verify that. So now GH times H inverse G inverse. So this should come out as the identity element of G. So you now use the associativity. So that is GH H inverse G inverse, right? So this is same as G E G inverse. So we can write it G inverse. That is nothing but the identity element. So let's also check the other side. So H inverse G inverse times GH. So we can write it as H inverse G inverse G H. So this is H inverse E H, and this is equals to H inverse H, and that is the identity element. So we are done. Okay. So for the third problem, so we need to prove the nth power of the element GH inverse is same as G nth power of H G inverse. Okay. So we will prove this by induction on N. Okay. So let's do it. So we will prove this by induction on N. Okay. So for N equals to 1, so for N equals to 1, if we go back to the problem, so you see if you put N equals to 1, so this is nothing but G inverse, and on the rather right hand side, it is also G inverse. So for N equals to 1, we have nothing to show. So it is just LHS equals to RHS. So now assume the result holds for N minus 1. That means if you take the element G inverse and take its n minus 1th power, that is same as G H power n minus 1 G inverse. So we need to prove for n. So now Let's look at the nth power. So we can break it as G inverse power n minus 1 times G inverse. Okay. Now the first part, this one is same as G h power n minus 1 G inverse. Okay. Now we will just use the associativity property. So G h power n minus 1 G inverse G times H G inverse. So this is same as G h power n minus 1 identity element of the group E H G inverse, and this is same as G h power n minus 1 H G inverse. So this is equals to G h power n G inverse. So this completes our proof. So these three properties we should remember always. First one is, if we take the inverse of G inverse, that should be same as G. Second is, inverse of GH is nothing but H inverse G inverse. The third one is, if we take the nth power of GH G inverse, this is same as GH power n G inverse. So these things will be used rapidly in other problems. Okay, uh, let's move on to another problem. Okay, so let G be a group and A, comma B, comma C are three elements of G. So we need to find an element X belongs to G such that AXB equals to C. So read the problem. So G is a group. A, B, C are three elements of G. So we need to solve this equation for X in this group G. Okay, so let's do it. So let me write down the equation. So it is given that uh, Ax b equals to C. So we need to solve it for X. So that means we need to found some value of X for this equation holds, right? So what we will do, we will multiply A inverse from left and we will multiply B inverse from right. Okay, let's see what happens here. So this implies A inverse XB times B inverse equals to A inverse C B inverse. Now by using the associativity in this left side, we have A inverse A times X times B inverse. This is same as A inverse C B inverse. So this is identity element times X times identity element. This is same as A inverse C B inverse. So that means X is equals to A inverse C B inverse. So we have found a candidate for the element X. So now let's substitute X in this equation, and let's see it gives the desired solution or not. So now A inverse C B inverse times B. So we are just substituting the value of X. So let's see what happens here. So again, by using the associativity, this is same as A inverse times C B inverse times B, and this is E times C again multiplied by E. So this is equals to C. So this X gives the solution of that equation. And one more thing, this solution will be unique. Okay, so if you take any other solution in place of X, that should be equals to this A inverse C B inverse. I hope this is okay. So meanwhile, if you have any doubts, you can ask me. Okay, so now let's do some more examples of groups which might be interesting to you. So this is supposed to be problem number 3, I guess. Okay, so prove the following sets are groups under the operation matrix multiplication. Okay, so let me write these sets one by one. First one is you take On of R and define it as A belongs to MNR. I hope you have gone through the first week lectures. So in that lectures, he has introduced the notations such that A A transpose equals to the identity matrix of order n over R. So this is basically the set of all n by n orthogonal matrices over R. Okay. So second one is let's put it as SO n of R. This is A belongs to ONR such that determinant of A is equals to 1. So this set is uh, some family of orthogonal matrices, specifically whose determinant is 1. Okay, and the third one is Dn of R. So this is basically A equals to Aij belongs to MNR such that Aij are 0 for all I not equals to j. So that means all non-diagonal entries of the matrices are 0. So basically this is the set of all diagonal matrices of order n over R. So we need to prove these three sets forms a group under matrix multiplication. So I hope you have no doubt in the definition of these sets. Okay, so the first one, ONR. So basically observe that all three sets are okay, and we need to assume one more thing. Sorry, for this third set, we need to assume AIIs are non-zero for all I. So we need non-zero diagonal entries. So then we can say all these three sets are subset of GLNR. So let me write down that. All these three sets are subsets of the group GLNR, and that is the set of all n by n invertible matrices over R. Okay, now let's do the first one. So for to prove this set is a group, we need to check the four properties of a group. So let's check one by one. So first we need to check it is closed under matrix multiplication or not. So let A and B be two elements of ONR. So that means A transpose is identity and B transpose is equals to identity. So we need to prove the matrix AB also lies in the set ONR. So for that we need to prove, okay, to show AB belongs to ONR, AB times transpose of AB. We need to prove this should be same as identity matrix, right? So let's use the properties of matrices. So this is nothing but B transpose A transpose. So use the associativity of the matrix multiplication. So this is B transpose times A transpose. So this is same as A identity matrix times A transpose. So this is A transpose, that is identity matrix. So this means AB also lies in the set. So ONR is closed under matrix multiplication. Okay. And second property is there should be some identity element of this set, right? So we can take the identity element of GLNR itself, which is the identity matrix. So now the identity matrix also belongs to ONR, right? And why is that? Because its transpose is itself, and this product is same as the identity matrix. And if we multiply any matrix A by identity matrix, then that should be the matrix A itself, right? On the other hand, this is same as identity matrix times A. Happens for every matrix in the set ONR. So clearly identity matrix serves as an identity element of this set. So identity n is the identity element of ONR. Okay. Now the third one is there should be inverses of every element. Okay. So, as we can see that the identity element is the identity matrix, and after multiplying by A transpose, it gives the identity element. So a candidate for the inverse should be A transpose. So let's check that. So we need to check the both side. Now for every A belongs to ONR, the matrix A transpose, it also belongs to ONR, because A transpose times transpose of A transpose, this is same as A transpose times A. This is follows from the properties of matrix, and this is same as identity, because that condition basically means A is an orthogonal matrix. So this should hold. So for every A transpose also in this set, and A transpose is same as identity element, and this is same as A transpose A. So from this we can say A transpose is the inverse element of A. So every element of ONR has inverse in ONR. Okay. So the final property is associativity, and that is trivial because ONR is subset of GLNR, and matrix multiplication is associative in GLNR. So it holds in the subsets also. Finally, matrix multiplication is associative on the set ONR, and this is because it is associative on GLNR. So all the four properties of group are satisfied here. So ONR forms a group. Hence ONR forms a group under matrix multiplication. Okay, I hope the proof is clear. Okay, so for the second one, we need to prove this set SONR, and this is subset of ONR, right? This is also a group. So here we have the one more property, and that is determinant of every matrix should be 1. Okay, so let's do it. So first we need to prove the closure property. So let A and B be two elements in SONR. So what does it mean? So it means A transpose equals to identity and B transpose, this is also identity, and determinant of the both matrices are same. Determinant of A is 1 and determinant of B is 1. So we need to prove the product AB is also SONR, is also in SONR. So now we know AB belongs to ONR by the first part, means AB times AB transpose equals to 1, and so one property is already holding. So let's check the second property, which is the determinant. Determinant of AB, so we know this is multiplicative, so that means this is determinant of A times determinant of B. So this is 1 times 1 equals to 1. So clearly it shows that AB belongs to SONR. So that means SONR is closed under matrix multiplication. So we left with 3 other properties, and that is follows from the first one, because again the identity element serves as identity element of this group, and inverses of the matrices are their transpose, and associativity property as it is holds here. So we don't need to check anything. So let me write it. Since the identity element belongs to SONR, and A times identity n equals to identity n times A equals to identity, sorry, it is same as A, and this holds for all A in SONR. So identity n is the identity matrix is the identity element for SONR. Okay, and for the inverses, since date of A equals to date of A transpose, and this holds for every square matrices, right? So A transpose belongs to SONR for every element A in SONR. Further, we have seen that A transpose is same as identity element, and this is same as A transpose times A. So clearly A transpose gives the inverse element of A, and this holds for every A in SONR. So A transpose is the inverse element of A in SONR. And finally, the associativity property holds because it's a subset of GLNR. So the matrix multiplication is associative in SONR because it is associative in GLNR and we have saw that SONR is a subset of GLNR. So finally SONR forms a group with respect to matrix multiplication. Okay, let's go back to the problems. So we have done the first one, also the second one. Now finally the third one. So we need to prove that the set of all diagonal matrices whose determinant are non-zero forms a group under matrix multiplication. Okay, so let's do it. So we need to prove the set of all n by n diagonal matrices over R, means whose entries are real number, forms a group under matrix multiplication. Okay. So let's quickly check the all four properties of being a group. First one is the closure. So it is a standard fact from the matrix theory is that product of two diagonal matrices is again diagonal, right? So if A and B belongs to DNR, so that means these two are diagonal matrices whose determinants are non-zero. So then clearly the product AB is also a diagonal matrix. So if you want a proof for this, you can go back to your matrix theory books. So is again a diagonal matrix, and determinant of AB is same as determinant of A times determinant of B. So this would be non-zero because all diagonal entries of A and B both are non-zero. So their determinants are non-zero. So this product should be non-zero. So that means AB belongs to DN. So the closure property holds. So DNR is closed under matrix multiplication. Okay. So second one is the identity element. So again, this will be same as the identity matrix. So let me just write it. So the identity matrix of order n, this is a diagonal matrix, right? Whose determinant is 1. And A times identity n, it is same as A, and this is same as identity n times A. And this holds for every element A in Dn. So that means uh, identity matrix is the identity element of Dn. Okay, so the inverse matrix. So for a diagonal matrix, so let A be a element of DNR. So we need to find a candidate for inverse of this matrix A, right? So that A inverse should be identity. So if you observe closely, A looks like, so these are just the diagonal entries and all other entries are 0. So what should be the matrix here? So after multiplying with it, we will get the identity matrix. So one natural guess is we should take reciprocals of di's, 1 by d1, 1 by d2, 1 by dn. Okay, so let's do that. Okay, so let me write the matrix A precisely. So let A equals to Aij belongs to Dn. So then the diagonal entries are all non-zero for all I equals to 1 to up to n. So consider the matrix B, which is Bij, as follows. So all non-diagonal entries are non-zero. So Bij equals to 0 if I not equals to j, and it is 1 by Aii if I equals to j. So then it can be seen that A times B is the identity matrix and it is same as B times A, and B is also in DN because it's a diagonal matrix and its determinant or the diagonal entries are non-zero here. So B is the inverse matrix of A in DN. So that means every element of DNR has inverse in DNR, and the associativity also holds because it is also a subset of GLNR. So let me just write down again the matrix multiplication is associative in DNR, and the reason is DNR is subset of GLNR. Okay, so finally this forms a group. Okay, so let me go back to the problem and let me ask you something. So here all these three sets ONR, SONR and DNR, all these three sets forms a group under matrix multiplication. Okay, that is what we have proved now. So first one is the set of all orthogonal matrices over R, n by n orthogonal matrices over R. Second one is n by n orthogonal matrices with determinant is 1. Okay, and third one is the set of all diagonal matrices. So my question is, any of the three groups are abelian? Can anyone answer this? So if you know, you can just unmute and speak. So is GLNR abelian group? So anyone from the participants? Okay. So one task is for you to prove that GLNR is non-abelian, and the first two sets are also non-abelian groups, but the third one is abelian. So I am going to leave that for you. So let me just put that as remark. Yeah, but there are some matrix groups which are abelian, right? So you can't say in general. Okay. Okay, fine. So let me put that as remark. So the first one is uh, ONR and SONR are non-abelian groups. Okay, let me put, so you can find it by yourself. And second one is DNR is an abelian group. Also, I can put a Y so that you can check it on your own. So this will follows from the matrix theory. I hope it's okay. Okay, now let me do some characterizations of abelian groups. So I guess this is problem 4. Yeah. Okay. So let G be a group. Okay. Then G is abelian if and only if AB inverse is same as A inverse B inverse, and this would hold for every elements A and B in G. So this basically says if this equation holds for every pair of elements AB, then our group G must be abelian. Okay, let's do this. So first assume G is abelian. Okay, assume G is abelian and A comma B be two arbitrary elements in G. Okay, we need to prove this equation holds. So let's start with the left hand side. So now A B whole inverse. So according to the first problem which we have done, let me go back. So if we use this property, so then we can write this is same as B inverse A inverse, right? Now our group is abelian, so we can just interchange these two elements. So A inverse B inverse. So the relation holds, right? So now let's do the converse part. So conversely, assume inverse of AB is same as A inverse B inverse for all AB in G. So we need to prove G is an abelian group. So for that, we need to prove that every pair of elements of G must commute. So let's take an arbitrary pair. So let G and H belongs to G. So what we need to prove is GH equals to HG. Okay, just keep this thing in your mind so that we can keep track what is our goal. So these are two arbitrary elements of G. Then by this given condition we can write inverse of GH is same as G inverse H inverse. So this is same as inverse of GH is same as inverse of HG. So this is again by using our first problem which we have done. So these two elements are same, and we know that inverse elements are unique, right? So if we take inverse of these two elements, that should be also same. So let's take that inverse of GH inverse. So that should be same as inverse of HG inverse, and both left hand side, both the sides gives our desired result. And we have taken GH arbitrary elements. So this holds for arbitrary elements. That means G is commutative. So we can say G is an abelian group. So thus G is an abelian group. Okay, I hope this one is fine. Okay, let's do some more characterizations of abelian groups. So problem number 5. So let G be a group in which square of every element is identity. So we need to prove G is abelian. Okay, so square of every element is identity in this group. That implies G is abelian. So we need to prove arbitrary pair of elements must commute. Let's take an arbitrary pair. Let GH belongs to G. Okay, so by the given condition, GH square should be identity. Okay, so if we multiply both sides by GH whole inverse, then what happens? Okay, let me write it. E times GH inverse, and this is same as E times H inverse G inverse, and this is same as H inverse G. Okay, now if you look carefully, the condition A square equals to E, that will imply A equals to A inverse for all A belongs to G. So use that property here. So this is same as H times G. So this is the required property. Hence G is abelian group. So one observation, that this condition square of every element is identity. So that implies every element is self-inverse. Okay. So both these two conditions implies your group should be abelian. So keep that in your mind. So meanwhile, any questions so far? You can ask questions from the first week lectures. I can try to answer them, but not from the first week assignments or second week assignments. Okay, so I have one more characterization for abelian groups. So this is problem number 6. So let G be a group. Then prove that G is abelian if and only if AB whole square is same as A square times B square, and it is holds for every element AB in G. Okay, I hope the question is clear. So this is an if and only problem. So we need to prove both sides, right? First, let G is abelian. And pick two arbitrary elements A, B from G. Okay, so we need to prove this relation holds. Let's see that. So now AB square is same as AB times AB. That is by definition of exponent of elements. So if we use the associativity, this is same as A, BA times B. Now we are in abelian group. So this element is AB. So A, AB times B. Again use the associativity. So this is same as A square times B square. So one part is clear. So we left with the converse part. So conversely assume this relation holds for every pair of elements AB in G. Then let's prove that G is an abelian group. Okay. So conversely assume AB square is equals to A square B square for all AB in G. Now let G and H be arbitrary elements of G. So we need to prove again GH equals to HG. So by given condition, GH square is same as G square H square. Now let's break both sides. So this is GH times GH, and this is G square times H square. Okay. So if we multiply G inverse from left, G inverse here and H inverse here, so we should get HG here, and in this side we will get GH. So let's do that. So G inverse GH, again GH. So we can use the associativity to write the brackets in any form which we like. H inverse. So right hand side also G inverse G square H square H inverse. So this is G inverse G HG times H inverse. This is G inverse G square. This is H square H inverse. Okay, so we are just arranging the brackets. Now let's see what happens. So this element is identity. This element is also identity, and this will be just G. This will be just H. So H E equals to GH. So that means HG equals to GH. So that is what we wanted to do. That these two elements commutes. Hence G is an abelian group. So there are some other characterizations of abelian groups. So for the time being, let's strict up to this for abelian groups. Now let's look some non-examples of groups, because so you have saw so many examples of groups, but a few non-examples. I hope in the assignments there are some non-examples which you can figure out on your own. So this one is problem number 7. So let X be a set, just a set, not a group. Okay, and G is equals to the power set of X. That means set of all subsets of X. So then prove that the followings are not groups. Okay, so the first one is the set is G and the operation is union of sets under union of sets. Second one is the same set G under intersection of sets. So these are two natural operations on sets, right? So let's just check under these operations the power set forms a group or not. So I have written it will not form a group, but we need to check exactly what property fails here. So any guesses that which property will fail? Okay, so let's start with the first one. G here, G equals to power set, and the operation is union. And we usually write union as this notation, by this notation. So let's check the closure property first. So let A comma B be two elements of G. So what does it mean? So it means A and B are both subsets of X. Okay. So since they are subsets of X, so their union should also be a subset of X. And that means this union should belong to the power set which is equals to G. So this is just basic set theoretic notions. So this shows G is closed under the operation union of sets. So G is closed under union of sets. So first property holds here. Now the second one is uh, existence of identity element. So here is your set X, let's say it is X, and you are taking a subset, let's say it is A. So what kind of element should be here that will give back you set A, and this is for all element A. Okay, hope you have understood this. So the obvious candidate is the empty set, right? If we take phi here, then A union phi is A for every A, and phi is also a subset of X. So phi is the desired candidate for the identity element. So now phi belongs to G, and A union phi is same as A, and it is same as phi union A, and this is for all A in G. So empty set is the identity element of G under union of sets. So phi is the identity element of G under unions. So first two properties hold C. So before doing the third property, let's see the fourth property, which is the associativity of the operation. So here the operation is union of sets, right? And from set theory we know that union of sets is associative. So let me write it. We know union of sets is an associative operation. This is from set theory. So fourth property also holds. So as we have written in the question that it will not form a group. So the third property should break here. That means there exists some element which has no inverse in G. So let's try to figure out that. So let A be an arbitrary element of G. So if B belongs to G is inverse element of A, then what should be? Then A union B should equals to the identity element, and that is the empty set, right? And this is same as B union A. So if A is non-empty, so if A is non-empty, then this union cannot be empty set, right? Because in the union then A union B also non-empty, because A is subset of A union B. So the element A cannot have an inverse. So every A which is not the empty set, does not admits inverse element. So immediately we can conclude if immediately we can conclude the set G does not form a group. Thus, G is not a group under the operation union. Okay, I hope this proof is fine. Okay, so first one is done, which is the union of sets. Now we need to check for intersection of sets. So this would be sets. Okay, so let's do the second one. So as it is, first we will check the closure property. So let AB belongs to G. So this implies our G is the power set of X, right? So AB should be subset of X. Since AB are subset of X, their intersection subset of A, it is subset of X. So intersection also lies in G. So the closure property holds. So G is closed under intersection of sets. Okay. Now second one is the identity element. So we need A intersection some element which gives A back, right? So what will be the obvious choice for this option? So that it holds for every element A. So that should be some bigger element of A. So it should be hold for X also. That means X intersection that element also gives X. So the obvious candidate is X, right? So let's write it. Now for every element A in G, A intersection X is same as A and is same as X intersection A. So X is the identity element of G under the operation intersection of sets. Okay. Now let's check the associativity property. Since from set theory you know that the intersection of sets is also associative, right? So we don't have to check anything since we know intersection of sets is associative. So intersection is associative in G. So out of 4, three properties are holding, right? So we are left with the third one, which is the inverses of elements. So let's check it. Now, for an arbitrary element A belongs to G, if there exists B belongs to G such that A intersection B is the identity element which is X, this is same as B intersection A. So if we take the empty set in place of A, so there will not exist any B which gives the intersection is same as X, right? Now for now let A belongs to G such that, so if A equals to phi, there does not exist any element B in G such that A intersection B which is same as phi intersection B, that is X. So the element phi has no inverse. Hence phi belongs to G has no inverse in G. So the third property breaks down. So G cannot form a group. So thus G does not forms a group under the operation intersection of sets. Okay, I hope this example is clear for you. So the power set of a set X does not form groups under union of sets and also under intersection of sets. So whatever example of matrix group we have seen, we have saw. So in that the identity matrix serves as the identity element, right? Now let's do one example of matrix group in which the identity element is different from the identity matrix. So this is problem number 8. So let G equals to the set of all 2 by 2 matrices such that A is a real number and A is not equals to 0. Then we will prove, prove that G forms a group under matrix multiplication. Okay, so we will see in this group the identity element is different from the identity matrix. So first check the closure property. So let A equals to this matrix and B equals to this matrix, and both belongs to the set G, so we need to prove the product is also in G. Now A and B are in G, that means A should be non-zero and B should be non-zero. Okay, now let's look at the product. So if you do the product, so this should be come out as 2AB. So all four elements are 2AB. And this element clearly lies in G, right? Because 2AB is non-zero, as A comma B both are non-zero. So this set is closed under matrix multiplication. So G is closed under matrix multiplication. So G is closed under matrix multiplication. Now for the second one, we need to guess a candidate for the identity element. So let A be an arbitrary element. Sorry. So A be an arbitrary element in G, and assume X equals to this element is also in G such that AX is equals to A itself. Okay, so this means, let's do the product again. So we need to solve it for the element X. So this product should be same as A itself. So in the earlier situation we have done the product, so it just become 2AB. So it will become 2AX in all four entries, and this is same as A in all four entries. Now just compare coordinate wise, means entry wise. So that will give you 2AX is equals to A, and given that the element small a is non-zero, so that implies X equals to 1 by 2 since A is non-zero. So our X is 1 by 2 in all four entries, and clearly this element belongs to G, right? Okay, and also A times, let's write another element, B times X is same as X times B is again B. This is for all B in G. So you can check by doing the matrix multiplications. So X is the identity element of G under matrix multiplication. So One thing you might have noticed here, that every element in this set G has a zero determinant, but still it forms a group under matrix multiplication. So, and the fourth one is the inverse. So, sorry, third one is the inverse of element. So, let A be an arbitrary element and assume AX equals to XA equals to X, the identity element. So, that means 2AX, sorry, our remember our X is 1 by 2 in all four coordinates. So, this product 1 by 2, 1 by 2, this should be same as 1 by 2. So in the left hand side, this is just a itself, because X is the identity element. Sorry, we have made a mistake, and we need to find the inverse, right? Okay, let's do it precisely. My mistake. And B be another element in G such that their product gives the identity element. Okay, so that means let's do the product again, and our identity element is 1 by 2, 1 by 2 in all four coordinates, and this product is 2AB in all four entries. So this should be same as the identity matrix, identity element, not matrix here. So if we compare entry wise, then it should be 2AB equals to 1 by 2. So that means B should be equals to 1 by 4 times A. So that means our element B is 1 by 4A in all four entries, and this element clearly belongs to G because A is non-zero. So we have found a candidate for the inverse element. So it can be checked that if the element A belongs to G, then its inverse is, then A inverse would be same as 1 by 4A in all four coordinates. And hence G forms a group under matrix multiplication. So hence G forms a group under matrix multiplication. Okay. So one thing you can check it by yourself, that this in fact is an abelian group. So this is different from the other examples of matrix groups which we have done in this season. So there the identity element is the identity matrix, but here the identity element is different from the identity matrix. Okay, let's move on to another problem. So if you have any doubt in this problem or in this proof, you can ask. Okay, let's do one example of a group. This one is interesting. So it is problem number 9. Okay, so let G be a group and suppose X be a non-empty set. Okay, now assume H equals to the set of all functions from X to G. So H is the collection of all possible functions from X to G. Now this set H will form a group under the following operation. So define okay. So for f comma g, two functions in H, define the product function as f dot g evaluated at small a as f of a times g of a. So here this multiplication is in the group G. Okay, so for a belongs to X. So then prove that H, then prove that H is a group under the above multiplication. The above multiplication. So I hope you have understood this question clearly. Okay, so let me read it once more for you. So we have started with a group G and non-empty set X, and we are taking H to be the set of all functions from X to G, and we are going to define a operation on the set H, and we are claiming H will form a group under that operation. Okay, so now let's try to solve this. So first one is as usual the closure property. So let F and G are in H. Okay, so we need to prove the product. Now F times G is also a function, is a function by definition, right? is a well-defined function by definition. So this product should lie in H. So H is closed under the operation. Thus H is closed under the multiplication defined above. Multiplication defined. Okay. Second one is the identity element. So we need to guess an candidate for that. So basically we need a function g for which this product will be same as f of a for all a. So that means g of a should be the identity element of g, right? So let's write it down. Okay. Consider the function I from x to g, which is defined by I of small a is the identity element of g for all a belongs to x. Then f times I of a is same as f of a times I of a. This is same as f of a times e of g. So this is same as f of a, right? This holds for every a in the set x. So this means f dot I is same as the function f. So similarly, one can check that I times f is also f, and this holds for which holds for every f in H. Hence, I is the desired candidate for the identity element. Hence, I is the identity element of H. Okay. So I hope so far it is clear and you have no doubts. Let's check for the third property. So let f belongs to H. So we need an element which serves as the inverse of f, right? And so let us define that element. If inverse from x to g be defined by f inverse of a, nothing but f of a. This is an element of g, so we can take its inverse. So then clearly f inverse is an element of H. That means it is a function from x to g, and f of f inverse is same as I, and it is same as f inverse of f. So you can check this one by on your own. So this implies every element f of H has a inverse in H. Okay. So every element has inverse. So the final property is the associativity property, and let's check manually. So let f g h belongs to h with three elements. Now, so what we need to prove? We need to prove f times g times h is same as f times g times h, right? So let's try to prove this. So f times g of h evaluated at a is same as f times g evaluated at a times h of a. This is by definition f of a times g of a times h of a. Now we are in the group G because all these three elements f of a, g of a, h of a are elements of G. So we can use the associativity of G. So we can write f of a times g of a times h of a. Okay. So this one is same as f of a times the function g of h evaluated at a, right? And this is same as f times g times h. Uh, let's put one more bracket here, evaluated at a. And this holds for every a in the set X. So this implies these two functions are basically same. Hence, the operation, the given multiplication operation is associative on H. Okay, thus H forms a group. Okay, I hope you have understood this proof. So, in fact, this is an abelian group. So, let me write it also. In fact, H, okay, sorry, this group need not be abelian. This is abelian if and only if the original group G is abelian, because we have defined this product operation using the operation of G. So I will put that as a remark. So remark is H is abelian if and only if G is abelian. Okay. So I hope you can do this on your own, or if you have any problem, you may put in the discussion forum. I am active there, or you may ask in the next tutorial also. So one more thing I need to mention. Let's go back to the problems. Yeah, the examples of matrix groups. So as I have told, this one is the group of all orthogonal matrices, and this is known as the orthogonal group of order n. So let me write that. I can put it here. Orthogonal group of order n. Okay, and this one is known as spatial orthogonal group of order n. Spatial orthogonal group of order n. And the third one is the group of all diagonal matrices. Group of all diagonal matrices. I'm sorry if I have messed up, but I hope it is understandable. So, yeah. So where? So yes. So the group H is abelian if and only if G is abelian. So let me write down. Okay. Uh, let me. Okay, maybe I can stop here. Okay. So we will start from the next week onwards. Thank you all for joining.